So hello, good evening to all. Welcome to the class. Today is the last class of this live interactive session. I have started this class right now because we have one new guest in our live session today. So before we start the class, I would request Mr. Tapendra Rawal to kindly introduce himself and share his opinion on what he wants to learn today. Okay, so it seems that he has left the meeting. No problem. Good evening, Mr. Prabhakar. How
Hey,
are
good
you?
evening, Mr. Banerjee. I'm fine. Yourself?
Yeah, I'm doing good. So, since we had a new guest and I scared him away, I guess. So, so let's not waste any more time and move on with the class. So today I do not have any specific doubts from your end or from anybody's end in that matter. So what I would do is first of all I'll discuss very slightly, very limited information I have on how the shear deformation is modeled
Before
when.
that, Mr. Banerjee, for this exams, do you have any sample previous papers? How it will be, the exams?
Oh no, I am afraid I don't have any. So
Okay.
um, so yeah, I don't have any sample as such, but I guess it will be similar to the assignments. Like it will not be very different from that. From my past experience in NPTEL, it is pretty similar to the assignments, but however, I am not sure.
Okay.
Um, so
Because they're
yeah.
not allowing this calculator. They're giving the online calculator. That is another difficulty in exams. Okay.
Oh, okay.
Okay.
But I
So,
guess online calculators are also like simple.
but
It's not very
but,
difficult.
but doing the matrix multiplications with a simple
Oh,
online
yes.
calculator, that is okay for
Yeah, like
practical.
I don't expect like many large calculations to be there. Basically, I as far as I know, in NPTEL courses the exams basically focus on the conceptual part mostly.
Okay.
So,
Okay.
but I'm
Anyway, I
not
just
sure.
asked that question.
Hmm.
Anyway, that's fine.
Yes, yes, no problem. So, anyways,
And
I would.
I
Yeah.
told you that as a week 6 assignment, that
Uh-huh.
option, whatever they are given in the solution and whatever was there in that quiz,
Hmm. Hmm.
both were not matching. So options, none of the options were correct in that were questions.
Oh,
One
so
of the
like in
question
the solution also they have given.
solution was correct.
Okay.
They are given it as a option A is the correct, and they are given the solution. If you
Hmm.
compare that option A matrix, global matrix, and that solution matrix,
Hmm.
one of the stiffness values was wrong in the options given. So
Oh, okay. Okay, okay, okay. So in that case, what did you raise any
I put that question in
issue?
that forum, but man, that's fine because I know the problem. Where was that? So I
Hmm.
sorted out that one. So that was fine.
Okay, I guess you will get the marking for that maybe, but I'm not sure.
But
Um.
I didn't submitted that whole assignment because
uh,
in that week I was busy in
Okay.
some of the office work, so I thought of answering at the end, but due to something I just, because generally
Hmm.
I keep that in Saturday Sunday time to
Hmm.
do
Hmm.
that.
Hmm.
So in that week, when I was solving that, I got confused with that answers, and then
Hmm.
I
Hmm.
tried couple of times. Then I thought, okay, let me answer that in Tuesday, Wednesday. Then I didn't get time in that.
Okay.
Okay,
Okay.
that's fine. So, but I know that where was the problem in that.
Yeah, so it's good to know that it's sorted out. So, yeah, so moving on to today's agenda is so first of all, I would give very limited information on that how the shared deformation is
Yes.
modeled. Hi, hello. Mm, are you?
Will there be some questions as in our exercises, sir.
Your voice is not clear. Can you
It's
please
difficult to
repeat your
pass, I think.
question?
Will there be questions related as usually as we practiced in our practice session, sir?
Mm-hmm. If questions were like in the examination.
Yes.
Yes. So I am not exactly clear on like what is the procedure for the examination, because I am not the direct TAs for the course. I am like separate. I am only involved with the interactive session, solving the doubts from the assignments. So, however, like it's my belief that usually the questions will be similar to whatever assignments that have been given and whatever concepts that had been, it will never be outside the concepts that has been taught in the class, and mostly similar to the assignment problems itself. I would request you to not worry. It will not be difficult at all if you have done the assignments properly, and if you have followed the class. It will be very easy. Don't worry. Okay.
And
Can you
another
give
question.
some information
Sorry.
about the exam, sir? Some of
Mm-hmm.
the time period. How can I manage in NPTEL exam? It's my first time, so I'm requesting you to answer this.
Information about the examination. So, I am afraid like I am not aware of the modalities.
Time management like uh, 3 hour exam we used to practice hard questions, medium questions. How will we these questions be answered in 3 hours?
Mm-hmm. I didn't get your point. Can you please repeat?
Uh, we're a little worried about the exam, sir.
Mm-hmm.
Can we get some information like how can we go through exam in 3 hours for this
Oh, okay.
matrix method, sir?
So, actually, like, have you solved the assignments and submitted the assignments in time? All the assignments that were given in the course?
Yes, sir. Yes, yes, yes. I
Okay,
have
okay.
submitted all of
So,
those.
so how much of time did you require for each assignment, like on average?
Some used to take long time, sir. 6 into 6 matrix used to be solved
Hmm.
for
Okay.
K, K group like this.
Yes.
Some used to take few times like choose option and tick
Hmm.
like that.
Yes. 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 Yes.
So how
So,
can I manage this? Can you understand?
yeah. 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 So,
So
yeah.
questions will be like I am expecting some of the questions will be from uh, our exercises.
Yeah, maybe it could be, but I'm not sure. Like, what I'm sure is like, one thing is that the examination is relative, I think. So if it is difficult for you, if it is time consuming for you, it will be time consuming for everybody. So on that aspect, you need not worry. Like whatever is the difficulty level of the examination, it will be the same difficulty level for everybody. So if it is time consuming for you, it will also be time consuming for others. And apart from that, I don't believe that very big matrices will be given to solve, because here the objective of this course is not to explain matrix algebra to you, or explain new ways or faster ways to solve matrix problems. Here the objective is to relate how matrices are used to find the structural responses under the given loading scenarios. So mostly I feel the questions will be pinpointed to the concepts that has been taught in the class. Some of the questions could be related to how you have assembled the matrices and how you have done those things. but to the best of my knowledge, it won't be very difficult. So please don't worry. If you have done the assignments properly, if you are well prepared with the assignments and you know the concepts, it will be very easy for you. Don't worry.
Thank you, sir.
Okay. Yeah. Um, and Mr. Prabhakar, you were saying something?
I think I forgot. Okay,
Mm.
I got this one. At the
Mhm.
end of this week 8, they started this basics of this finite elemental method.
Yes, yes,
Okay,
yes.
so in which course you suggest for civil engineering? Because I saw that in the oral there are 3-4 courses in that finite element method. So
Oh.
because that is applicable for all disciplines. So it should not end up in happening that enrolled for some discipline which is not related to civil and structural.
Hmm.
So which course
So, like
will be
you are talking about finite element
next course? Yes, finite.
in.
If I want to pursue another course in the finite elemental, so
Hmm.
which
So
one
in
you
NPTEL itself.
recommend in NPTEL? In
Hmm.
NPTEL.
Okay, okay. So I am actually not exactly aware of who are conducting the courses, but
Hmm.
what my suggestion would be, like, whenever you see the course, you can go back to the course instructor. You can find that the course instructor
Okay.
is in which IIT and is in which
Okay.
discipline. So most of the times that will give you the idea, like whether he is from a civil engineering background or a mechanical engineering background or
Exactly.
similarly. Yeah.
Got it.
So, yeah, yeah. So yeah, and so are there any more questions right now?
No.
No. Okay. So as I was discussing, the today's class, I will first very briefly introduce about how the shear deformation is incorporated in the software packages, and then I will give a very brief overview of the finite element method. I feel that the last week's lectures were like pretty heavy, I guess. So means as compared to the pace in which the lectures were moving in the first 7 weeks, as compared to that, the introduction of finite element method had a lot of new things, many new things. So I don't expect like everybody to understand most of the things. Even I may not understand many of the things because I am not a active researcher in that domain. However, like, I have tried to summarize it in a very short format, just to give you the idea on the development of, like, how we are moving forward to the matrix method to the finite element. Actually, obviously, that is what it is taught in that last week's lectures. However, I felt it would be good if I could give a short summary again, so that you can recall some of your doubts while listening to the lectures, and maybe if I'm able enough, I can solve those doubts. um, so that is the second agenda of today's class. The third agenda would be to solve the last previous year's assignment of week 8, okay, which I don't think will take much of a time. And yeah, so right now we have only one participant. uh, I guess the other participant had actually come to know if some of the questions were available for the exam. I don't know, but let's start with today's class then. So, the first topic for today's class would be discussing about the shear deformation mention in software packages. Last day we had actually uh, discussed about what is shear deformation and how it is calculated using the energy based methods. However, quite evidently that is not maybe how it is calculated in the software packages. So I did a little bit of deep diving into that topic. However, like, one disclaimer, I did not get any uh, any documentation for STAD itself. So I tried to look for some documentation for STAD, but I was unable to get some. So instead, what I did is I found some documentation for SAP 2000. I feel you are aware of SAP 2000. Um,
Yes, but I have not used that. We are mostly 90% we are using STAT. We are not using SAP.
yes.
Myself. Okay.
Yeah. So basically, they are pretty similar software packages. Objectives and the most of the things are pretty similar. Only using two different um, parent companies. However, the structure analysis part and metrics and even the graphical interface to some extent, they are pretty similar to each other. So in my understanding, whatever SAP 2000 would be using for its modeling and analysis, TAD would be using something very similar to that. Apart from SAP 2000, I also searched some of the uh, one software package called Stera 3D, which is actually quite famous in Japan. So currently, as you might recall, that I am in Japan, and my immediate supervisor in Japan, he has developed one software called Stera 3D, and he uses some of the he has like the software is pretty similar, like not as advanced as say STAD or SAP, obviously, but it has quite good features, and it is capable of doing all those analysis on a much simpler basis. So in that software also I verified, and I found that it is pretty much similar on what SAP 2000 has also considered. There are some differences, but we'll not get into that. uh, only thing is like very limited information I have, and I want to give you that in this class. So basically what happens is, we have this equation: the force vector equals to the stiffness matrix equals to the displacement vector. Okay, so currently what we have done is, we have considered this for bending, elastic, deformation. Elastic is like constant for everything, but bending, deformation, we have ignored all the other types of deformations. So what has basically happened is, we have found the stiffness matrix for bending, and the displacements we have assumed is for bending displacements. We have not considered any other displacement or stiffness in this case, in the current scenario. However, like if we want to find the deformation due to shear, what needs to be done is, we need to find what is the shear stiffness and the shear deformation, right? So this is what is required for the shear deformation. Similarly, if we see, there could be also torsional deformation, right? So we are neglecting all of these parts. However, in the softwares, they have the provisions for calculating these things, right? So our aim is to find out like what may be the underlying philosophies behind this. So basically in softwares, what I saw is, to find the to find the shear stiffness. Um, okay, before we do that, let's recall how do we find the bending stiffness KB. Say only KB, not the matrix, only KB for say a linear bar element, which has say like this, some u1 u2, its length is L, something like this. Then we find a stiffness like KB, we find say k of 2 with respect to 1, or 1 with respect to 2, like this, right? So what basically do we get in that? We get AE by L. AE by L is the stiffness of any one point with respect to the other point for a bar element. This is clear?
Yep.
Right.
Yes.
Yes. So if we try to get an analogy to this, like if we try to get what could be the stiffness, what could be the shear stiffness with say same 2 1 1 2, obviously the deformation will not be like this. The deformation would be something like this. Say here it is downwards, here it is upwards, something like this, u1 u2 something. Okay, this is the bar. So if we try and get a similar kind of stiffness, elemental stiffness, what would be the like what could be the stiffness? Any idea?
Is it something related to shear modulus, G?
Exactly. So it will be something related to GA by L, right? But this A will be different. G, how do we calculate G? We sometimes calculate G equals to E by say 2 into 1 plus nu, right? Where nu is the Poisson's ratio. So you might remember that while defining the materials, we also define its Poisson ratio in the software, right?
Correct.
So from that you can find the estimate of the shear modulus of the section, right? This A, for the timing, let's keep aside A, but A is what could be A? Like what do you feel A should be?
It would be shear area.
Shear area, right? So basically if you can find out the shear area, you can find out the element stiffness, and once you find the element stiffness, you know that it's not very difficult to arrange it and find the global stiffness matrix, right? So basically the most important thing is the shear area. And the shear area, what I found is, like, for this is source from CSI documentation for SAP 2000. Shear areas are like effective shear areas are found for different kind of cross section, right? So we have all the defined cross sections, we know the effective shear areas for that, which is fed into the software. Apart from that, there are other cross sections also, like this one, this cross section, this has some like different terms which has the formula to find the effective shear area. Now the calculation of the effective shear area, I am not touching it even a little bit. It is a part of the solid mechanics or strength of materials course, the effective shear area and all those things. My objective here is to just give you the idea that how maybe the shear stiffness can be calculated by using some effective shear area and some shear modulus, which can be calculated using the elastic modulus and the Poisson's ratio. So this is how you can find the elemental shear stiffness, and this is how you can formulate the whole matrix. But like, is it now realizable that this can be done in software?
Yes.
So
So then
basically,
how they, I mean, they do two, finally they'll add both the forces, shear deformation force and
no, yeah. That was my like final point in this discussion. So finally, like, now we know this is for bending, this is for shear, this is for say torsion. So what they will finally do is they will find the final displacement as displacement due to bending plus displacement due to shear plus displacement due to torsion. The forces are same in this case, but the displacements are added, and these two displacements currently we are neglecting. So we only use this displacement due to bending, but this is also considered in the our what to say in the softwares. Okay. So this
but
is
that F is what, shear force or what it is in the second equation?
which one? F? F here. Okay. So even for bending, we have the F as the shear force and the moment, right? So even for shear stiffness, we can find the shear force and moment to calculate what are the shear deformations. Like, these degrees of freedom can be used as same as the case of bending itself. Okay.
No, my question is, when we find the responses of the different elements, we are doing separately for bending and separately for shear, then we'll add both the forces.
Yes. And F is the, like, F is the shear force and bending moment, like similar to what F we had in the case of bending deformation. We had some forces like this and moments like this, right? at the
Correct,
two
correct.
node points.
Hmm.
So same forces and moments will actually contribute to the shear deformation as well.
Exactly.
Yeah.
Then they will add it. Then they will add that.
Yes, yes, yes.
Okay, okay.
So this was what I found about the usage of shear deformation in different softwares.
So
And
you're telling there will be different global stiffness matrix for bending as well as different global stiffness matrix for shear deformation.
yes, yes, yes.
It is not
This
a combined one. It is a separate
yes, yes,
stiffness
yes, yes,
matrix. Okay.
yes, yes. And also, like, for further reading, I would recommend you can just search this CSI documentation for SAP 2000. This is the technical manual for SAP 2000. This is freely available in the internet. So you can just search this, and this has all the basic theories behind all these things. Not only shear deformation. So I am not sure why I couldn't find for STAD. There is also some
STAD also
documentation.
should be available. STAD also should
Yeah,
be
STAD
available.
also should be
In the
available, but
technical manual should be available in that.
right. So you can
But
go
anyway,
there.
if I find that, I mean, I'll have that. I'll share it with you.
Yeah,
But
sure.
only thing is that whatever you said that Poisson's ratio,
Yes.
defining the,
Hmm.
but for our bending thing, Poisson's ratio will not have an impact, right, for our analysis.
For bending, no, it is not coming anywhere in the bending equation.
So in that case, if I don't define that Poisson's ratio, say
Hmm.
zero or something, probably it should ignore the shear deformations in the analysis.
Oh, I'm not sure about that
Let me check that.
because
I'm just, when you said that, I'm just thinking that because these are the inputs what we give it in the stat.
yeah, 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 yeah. But
So
this Poisson ratio, if you give zero, I am not sure. It might take the shear deformation as e by two, putting Poisson's ratio as zero. And Poisson's
okay.
ratio also has some like feasible limits also. So any
Oh,
kind of
that
Poisson's.
formula it is e divided by 2 into 1 minus. So if
Yeah.
it's 0, it takes still it calculates with respect to e by 2
Yeah,
and
yeah, 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 yeah.
could be.
And
Let
apart
me.
from that, you can also give your own G value, I guess, in the software, like uh, forgetting about the Poisson's ratio. So that is
Okay, fine.
also possible.
Got some idea on that. Let me try that. Thanks.
Yeah, yeah,
Thanks for that, Mr. Bennett. Thanks for
yeah.
that.
Okay, okay. So this was all about the last previous discussion. Now I will quickly like go through the an overview of finite element method, and then I'll quickly discuss the assignment problems, and we can end the class. um,
Okay, before that, still I'll
yes,
go back to the last week's discussions.
yes, yes, please.
Uh, that transformation matrix and the element stiffness matrix for the column element in a
Hmm.
frame.
Hmm.
Okay, so I was telling you, I mean, do we need to interchange that stiffness values in the axial direction or the
Hmm.
vertical translation?
Hmm.
But do you think it will be better instead of calling this whatever that U1, U2, U3 or whatever that, is it better to call it with respect to a suffix with respect to x-axis, y-axis or xy plane? That makes sense?
uh, no, actually,
Because that remains the same, whether it is a beam element or column element,
hmm. So but
that
actually
x-axis remains the same.
actually, yeah,
So then we'll not
yeah.
get confused with respect to, because when I start writing the, okay, you're right. Finally, with the transformation matrix, we'll be converting into a global thing. It
Hmm.
automatically shifts that into proper. Otherwise, what happens when I'm writing the stiffness matrix for a column element?
Hmm.
Suddenly, I'll get the first term will be AE by L. I'll get confused because in a column element, that will be perpendicular to that beam axis,
Hmm.
that AE by L term. So why authors are not using that XY or XY plane suffix, so that if they use that will be easy
Yes.
to, I don't know. It is just, I'm just thinking. I mean, I may be
So
wrong.
uh, so yeah, so what is happening here, I if I could say in a very like different way, is that actually what is happening is, since you can see the column and the beam, like this.
Mm-hmm.
So your brain is working like this is how it should be. So
Mm-hmm.
because you are smarter than the computers, you can quickly relate. But the
Exactly, I
devil,
understood that. I understood,
yeah,
completely understood that. My only limited point is, in the textbooks or anything, will it be better if they add that X, Y suffix so that
uh,
students will easily, they'll not.
no, actually, I would say why it is not used.
Okay.
So, so currently, what is happening is like this is 1,
Hmm.
this is 2, and this
Exactly.
is 3, right? And okay, I will break
Now
it
it will be
down.
other way around. Two will be,
Here it is
if you
1,
consider
it
beam,
is
yes.
2, it is 3, right?
Yes, yes,
This is
yes,
for element 2, this is for element 1. So this is why you are like it is confusing for you, right? So you
yes.
are saying that maybe if we could use uh, like this, maybe
Starting
if we
initial
could
node in the
use x,
UY and the UXY and
y,
end.
z, and same x, y, z. So this is your point, right?
Yes, that makes sense, right?
Yes. So but now, because this comes to your mind because you can see the column, like column and beam. So what happens in, say, mm, what happens in, say, a frame like this? So in that case, through your logic, it should be x like this, y like this, z like this, and then x like this, y like this, z like this. So in this case, to find the
Okay.
stiffness matrix itself, you have to first
Okay, got
transform
it.
the,
Got your point.
yeah.
Probably they're relating with the local axis along the
Yes,
longitudinal
yes,
member.
yes.
They're taking as X and perpendicular to that they're taking it as Y. Okay.
Yes, 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 yes. So, this is actually because like this is some problem you are solving by hand, but you are developing the method to not solve by hand, right? So you are developing the method so that you can instruct the computer to do it for you. Now the computer doesn't know which is a column, which
Agreed,
is a
agreed.
beam.
Got the point. Got the
Yeah,
point.
yeah,
So
yeah,
when we are deriving that beam element matrix, it is for the local axis,
yeah. Yes,
considering X
yes.
is along the longitudinal axis and Y is perpendicular to that.
Exactly, exactly.
Whether it is a column or beam, that remains the same. So
Hmm,
when we write
exactly.
that stiffness values, always you have to, first term will be AE by X along the X
Yeah,
axis,
yeah,
local
yeah.
X axis. Okay,
Hmm.
clear.
This
Clear,
is
Mr.
just to
Ramesh.
give the uniformity to the whole madness,
Got it, got it, got
method
it,
to the
got it.
madness. Yeah. So okay, that is done. Now a brief overview on like the finite element method. Mm, before the finite element method, mm, what in this course, in the matrix method course, what we basically did is like we took various frame structures, various different kind of structures, and then we broke them into different elements like this, and then we found the different, say, uh, deformations and stuff at the different nodes of the elements. Okay, like this. We did not focus on what is the deformation inside the element. We simply assumed like we want to find only the deformation at the different nodes of the elements. Okay, and without any consideration on the deformation within the element. Okay, and but still, like one thing which we did is like we broke it down into elements. That is very important. Like this is very similar to the finite element method. We break the whole thing into elements. Okay, but in this way we did not bother about getting the different deformation throughout the element or taking the effect of the discretization into the problem. Uh, in finite element method, what is added here is like even this one element you can break down into different pieces, and then you can get a much finer, like much what to say, uh, so you can even get the different so now if we break down into these small elements and then assume that each element is rigid by itself, then you have displacements and these things at deformation at different nodes again, but now you also have the deformation within the larger element. Okay, so without solving the element analytically, like what is the best option? Our best option is to like draw all the forces, everything, bending moment, everything, and find out what is the actual deformation point by point. But this is not easily possible for every kind of structure. Maybe for portal frame it is possible, maybe for some kind of even some complex structure it is possible, but it is very difficult for like very complex structures um, like it is easy to break it down into elements for say frame, a building maybe, but what about a aeroplane, right? An aeroplane, breaking down an aeroplane into elements is very difficult. Every part of its body is very has different curvature and many things associated to it. So what do you consider as an element? And it has uniform mass throughout its body, like a shell. So it is very difficult to break down that into elements, right? So in that case, what can be done is, say you have very curved surface like this, something, you can break down into small parts, and you can just try to find uh, what is the like um, what is the response of the structure at different points, which are the nodes connecting the different elements. So basically what we want to have is we want to have information on each node, and through this, like only knowing about this, like you can break a very big structure to various nodes, say. Only by knowing this one you can understand one concept that was taught in the class, which is like very important concept in finite element method, is that okay, I will expect this answer to from you. Like you have a continuous kind of element like this, okay, continuous, and this is finite element discretized structure. Okay, this is finite element discretized structure, this is the continuous structure. So which one would be more stiff?
Definitely, continuous one will be the
More stiff?
No, sorry. Yeah, finite element and individual elements will be more stiff.
Yes, exactly. So finite element will be more stiff, because in finite element basically what is done is like kind of we discretize the whole domain into small elements which are uh, which are inherently rigid. Like maybe you can say that maybe we have a bar element, and we consider a higher order polynomial. So I hope you have already gone through the videos, right, for week 8.
Yes.
Okay, so you know this, right? So you have a bar element, you have two points here, two nodes, and you have a linear kind of polynomial, like a linear variation of the deformation. So you can say that if I add one more point, I can have say a polynomial like this. So why are we calling this rigid? Like this is not a rigid body anymore. Okay, but who knows that the deformation of this is not this? Like who knows that it is not a even higher polynomial? So what is the point to which we go adding nodes to the element, or we make the element smaller and smaller? So there is no end to that, right? So so eventually you have to like agree that your element will actually make the structure stiff. So that is the reason why it has been discussed in class that like no matter how many you increase number of elements, or increase number of elements basically means the increase the H convergence factor, right? uh, I do you remember about the H
Yes,
convergence
yes, yes,
factor?
yes.
Yeah.
H and P convergence. Yes,
Yeah.
yes.
So H and P is basically, if you have say a triangle and you find the size of the triangle as H, if you reduce the H and increase the H convergence, and if you have different points, say three noded, then if you increase nodes and make the element more nonlinear in nature, then that is P convergence. So if you increase the H or P convergence, then basically what happens is that your solution actually converges like this. So if this is the displacement, actual displacement, then your displacement is very less, because here it is very stiff, and as it goes this side it becomes flexible and flexible and tries to approach the actual solution. So this is the basic one of the like features of finite element method, which I felt that it is
But how
like
do we decide that how many elements we have to make?
yes, exactly. So that is the like H convergence factor. So first
I
of
think
all,
that was not there in the class. That was, I think, I don't think that they touched that topic in the last
uh,
week's
okay,
thing.
yes,
See,
uh,
for example, what happens in general in practical field?
mm-hmm,
I've got a one complete raft foundation
mm-hmm,
where that column locations are not symmetrical. Okay,
mm-hmm,
if it is symmetrical, I can take one strip and I can analyze that. I can give that instead
mm-hmm,
of. But what happens in some of the structures, that column locations will not be symmetrical. I cannot take any contributory width or anything to arrive at the bending moment and shear force
mm-hmm,
in that.
mm-hmm.
In that case, what we do, we design using a plate elements
Okay, yes.
instead.
Mm-hmm,
Okay, so we take all that load, we put combination, we make a different plate element. Say for
mm-hmm,
example, in power plants, your boiler foundations may be in the range of 40 meter by 50 meter or
mm-hmm,
something, uh, with some 20-25 columns here and there in a
mm-hmm,
irregular locations.
mm-hmm,
So, and that thickness will be 1.8 meter, 2 meters, huge foundation it is.
mm-hmm, mm-hmm,
So in that case, what happens? We will not be sure what could, what will be the element size which gives us the correct,
mm-hmm,
near to accurate results.
mm-hmm.
See,
So,
generally what we do, we
mm,
assume that okay, thickness might be 2 meter, we go by 2 meter by 2 meter aspect ratio, and I mean, we might be wrong in
mm,
that cases, because what happens in 30 meter, if you make only 2 meter by 2 meter, you get only 15 elements in one side,
mm,
15 by 15.
mm,
I feel it might be less.
mm. So
It
what
just
what
goes by our judgment.
so
So
what is usually done in these cases?
I know that's what I said. We'll go with that thickness, assuming 2 meters. So we take that aspect ratio to keep that 2 by 2, and there'll be a lot of arguments in that.
Mm-hmm.
Finally, what we do, if we are not satisfied, we'll go with some 0.5 elements and 1 meter. We'll check the results, and
Mm.
if it is converging or something, it goes with a trial and error basis.
Yes, yes, yes. So
Okay,
basically,
so we'll
yeah.
take the maximum bediment and shear stress values with
Mm.
we do some 3-4 iterations. What
Mm-hmm.
happens if it is 2 meter, 2 meter? What happens if it is 1 meter? What
Mm-hmm.
happens whether it is a large variations or it is converging?
Mm.
So finally we we conclude, okay, go with that and add some factors and give that design. Okay, it is matching somewhere
Mm.
in that number. We'll not have the exact values
Mm.
for that. If it is regular column locations, we'll take the contributory width and we'll put a bend event share. We know that exactly.
Yeah.
Even that may not be a correct value, but
Mm-hmm.
psychologically we feel okay, that is a value what it should come in
Mm-hmm.
that. But when you do that plate elements,
Mm.
we have to do these iterations and we have to
Mm.
uh, in for those results there.
Yes, yes, yes. You are like you are absolutely correct. First of all, like just a disclaimer that I am not at all knowledgeable about
Agreed,
finite
agreed.
element
Actually,
method.
you already
Uh,
said.
yeah, yeah.
I mean,
Uh,
it is for your understanding. If you come across any such situation, you can
yeah,
just
no,
give in
no.
the
Yes,
practical what
yes, yes.
happens in the
So,
actual.
having said that, I have already like you can find one paper of one conference paper from me defining some finite element model of some isolator. Okay, so so what happens is like so basically whatever you have said, that is correct. So like in research what we tend to do, I am not aware of like what happens in, means maybe raft foundation or some very general structures, they could have a method to finding the like minimum size, maximum size, those things. Okay, so that you can like go through literature or come across some literature which have mentioned that you can use this size for this type of foundation, something like that, which I am not aware of at all. But basically from a research point of view, you are absolutely correct. Like whenever we are doing finite element models for new kind of devices, new kind of geometries, new kind of material properties, new things, so in that case we always check for the mesh convergence. We call it the mesh convergence. So what is basically the mesh convergence is like we reduce the h value. So we reduce the size of the elements. We exactly as you have said that we assume something. We assume from like experience that it should be like around this value. Then we go to smaller, 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 and then finally when we see that this kind of convergence actually comes for every problem, when we see that this kind of convergence has occurred, like when the rate of change is like falling, it's not very much, so then we decide one value that okay, this is some value which we are considering as very close to accurate. But you can never get the most accurate value that is already given. And mostly what we do is we conduct this mesh convergence study to find out what is the like appropriate size of the mesh of the different elements. So I would suggest the same thing, but I don't know, maybe for rough foundation there could be some formulation or some empirical formula kind of thing. I am not sure whether there could be any actual formula, but maybe some empirical formula could be
It's
there.
only just iterations because no, I mean,
Yeah, basically
whatever the size
iteration.
you
You have
give,
to do
the,
iteration.
the person who is approving that he will have thousands questions on that. Why it is only 1 meter by 1 meter? Why not 0.5 meters?
Yes.
So those questions. So
So
for that, we'll keep all these backups. No, we did all the
yeah,
iterations. So this is
exactly.
where we are converging, and okay.
Exactly. This
But
is
we'll
what
not
is
include every. We'll not include all the results in our report.
report.
We'll include.
Obviously, yes, yes,
We'll
yes.
keep it as a backup. Okay, this is what we got the results. So
Yes, yes. This is basically what is also done in research. Like even in research papers, you will find that in papers which are using finite element method, they have written that the like suitable mesh convergence study has already been conducted, and these results are from the converged mesh, not from any mesh.
because
So
that thickness of the draft, I don't think that matters for any of these analysis results.
yes, exactly.
Correct.
And all those
Correct.
things you have to know from experience, like which size will matter, which will not
Yeah,
matter,
because
and those things.
if I see that it's a theory, plate element theory, it takes only that axial force
Depends
and
on the
shear.
exactly. Hmm.
Yes, okay. Definitely, if you
Depends on
increase
the
the thickness,
element type
automatically
also.
shear stress will
Hmm.
reduce. If you increase that, depending on the thickness,
Hmm. Hmm.
your shear stress will reduce or increase depending on that thickness.
Hmm.
But that will have any impact on the overall H factor, H convergence, or
Hmm.
nothing. But anyway, we have to
Hmm.
do these iterations and you have to
Yeah, yeah,
do
yeah.
those.
At least you
But
have to do some iterations, and this will also give you some like idea for future problems as well, like where to start actually. And also the thickness and those things also, it also depends on the type of element you are using. If you are
Hmm.
using plate element, there is like not much meaning of the thickness, because it will itself not consider any strain or these things in the thickness direction. But if you are using solid element, that will have some effect on the thickness. So also so it is tricky. Like finite element method is not so straightforward. Like then which element should we choose? So solid element may give us more better results, but it is not needed. So why would you choose solid element?
Yeah,
So
generally we don't use solid element except in some dynamic analysis where we had to
mm,
take out those frequencies and amplitudes. So for
mm,
compressors or turbine foundations,
mm,
there we go for these four node solid elements.
mm.
Otherwise, for all these things, we'll go with the raft foundations and all. We'll go with the plate elements
Plate
and we'll.
elements. Mm, mm, mm,
Because in that we'll not get a, I'm not sure in the 3D solid elements, I don't think we get a proper bending values or the shear. I don't know. I need to just verify that why we are not
mm.
using that. We use only for the vibration analysis for
No,
that.
no. I feel that you will get the proper values, but again, then again, question will come like,
It's not required. It is not
it is
requisite.
not required exactly,
It
and
is
if
not
it is not
requisite.
required, if it is not required, it is not advisable to go for if you just only go for the highest possible polynomial and highest possible element dimension and those things will not always help. Maybe they can also sometimes take you away from the results also. That is different. However, it is always preferable to keep it simple and know the physics also behind the solution. Yeah.
Okay.
Yeah. So anyways, so now so what happens is, like in finite element, yeah, as I was talking about, that the whole domain is then discretized into various small elements. Now our objective here is, from the matrix method of analysis method, our objective was to find the stiffness matrix, right? If we find the stiffness matrix, we note the forces, and we can find the displacements. So similar to that, objective in case of finite element method will be again to find the global stiffness matrix for this many degrees of freedom. Now we have a lot more degrees of freedom than only those specific elements in case of matrix method. So how is that stiffness matrix formed? That already it is discussed in the class, and I will give a brief overview of the most simplest problem. Okay. So considering, say, a solid element like this, okay, what are the different for stresses in the element? We have sigma xx, sigma yy, sigma zz. These are the axial stresses. Now now the shear stresses, this is tau xy, this is tau yz, this is tau zx. These are the shear stresses. So you could have some stress vector like this: sigma xx, sigma yy, sigma zz, tau xy, tau yz, tau zx, right? So this is, say, the stress vector, and you can also write the stress in tensorial form as it has been shown in class, like a stress as a matrix.
I was about to ask that. What is the difference between vector and the tensorial form? Why it is a stress tensor and stress vector? What is that?
Basically,
Probably I'm asking a too basic question, but
no, not at all. Very even I am not sure of what is the uses of the tensor form or vector form, but from basically a
what is the
mathematical.
physical meaning tensor? What is that tensor form means basically? Is it
Ah,
just a terminology or
it's just a like to the best of my understanding, I only understand it as a term, right? I don't know what is the physical meaning of that. Basically, in the tensor form, it is represented like this. So one of the reason is like okay,
If you
I'll
put it in
just
matrix, do we call it as a stress tensor? If you put it in a matrix, I mean,
yeah, we if we put it in a matrix, it is called the stress
like we call it as a
tensor.
stiffness matrix and a force vector. That stiffness matrix, we'll call it as a stress tensor if it is in that form. Is it?
uh, yes, but this has some special meaning, like this tensor, like but why do we need to go from the vector to the tensor? That is one like question, right? So what happens is that when we have the vector, we assume that tau xy equals to tau okay, sorry, here everything is written in terms of sigma. See, so sigma xy equals to sigma yx, right? We assume that is same. Now why
Yeah,
can we assume that? Is there are many assumptions in the material, like it is isotropic in nature and
exactly. Yes.
those things. So actually, if we break down into each and every component, and if we don't assume anything, so it will be kind of a matrix, the stress values. Like it can be arranged as a matrix, only seeing the different axis in which the stress is acting. Okay, different axis. But however, if we consider this to be isotropic and then
Then it becomes
homogeneous
vector
and
form.
those
Then it
things,
becomes vector.
then it
Then
is
it becomes vector
compacted
form.
and it becomes the vector form.
Vector form.
Exactly.
Okay. Okay.
Yeah.
Got it. Got it. Okay.
Yeah.
Good.
So for finite element, I guess in advanced courses they only use the tensor form again to like generalize all the things. Most of the objectives, like main objectives here, are to generalize things, so that we don't have to do it. We can instruct somebody, the computer, to do it. Anyways, so this was the stress vectors, stress tensors. Now again, the strain vectors would be something like this. Same thing, like only in a different, using a different kind of denotation. So now what we know is, for this solid element, the strain can be written like this: epsilon xs equals to what? If we say, if the body moves in this direction as u, this direction as v, this direction as w, okay, there is a like display deformation in these directions. So epsilon xs will be, xx will be del 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 u by del x. Okay, epsilon yy would be del v by del y. Epsilon zz would be del w by del z. Now epsilon xy would be half into del vy del x plus del u by del y. Epsilon yz would be half into del w by del y plus del vy del z. Epsilon zx would be half into del u by del z plus del w by del x. Okay, so these formulas, so can you say what are these relations?
This relation means it is a strain relation.
Strain relation
En-
with what?
en- Energy, strain energy,
Strain is related to like which variable here?
energy, strain energy.
No, like
No,
here what is happening is like the strain is calculated using the deformations
Deformation.
Yeah. So these are the strain displacement relationship. These are the strain displacement relationship. Now, before going into the all these, just a comment on why we are doing these things. Okay. So the reason why is we know the constitutive relationship, right? You know what is constitutive relationship?
Yeah, I mean, which relates the two functions, how it is related, two variables.
Yeah, to which two variables, like two specific variables it relates.
Yes, in matrix, I mean, force and displacement, the stiffness matrix is a constitutive relationship between force and displacement,
Okay,
right?
okay, okay. Like force and displacement, yeah, but that is like a derived relationship. This is actually called the constitutive
Stress and strain,
relationship.
stress and between stress
Stress
and
and strain, exactly. So, this relation is actually called the constitutive relation. Now we always know what is the constitutive relation in different scenarios, right? We can always say how this stress is related to the strain, and how we can say that from the material property. If we have say different material, we know it is elastic, we know it is something anything, but we know this relation, like what is the relation between stress and strain. Okay. And using this property of the material, I want to go back to the force displacement relationship. So why? To solve the deformation due to the given forces. Okay. So to do that, what we need to do is, like we have strain here, we have to eliminate this strain and bring in displacements here. Okay. This is one step. And we have to eliminate this stress and bring in forces here. Okay. So this is the basic, like this is the essence, like this is the source equation. The constitutive relationship is the source. From there we want to go to the force displacement relationship to model our structure in finite element or any kind of method. So we want to go from the strain to the displacement, so the strain displacement relationship, and we want to grow from the stress to the forces. The stress to the forces, it is simple. In case of say bar element, in a bar element, what is the stress to force? Stress equals to force by area, right? Very simple. But in other than bar element, say just for example a beam bending problem in an elastic beam element, it is not that simple. You cannot like directly go to the shear force to the stress to the bending stress, right? You can maybe go from the moment to the bending stress by my by I, those formula. But how will it go from the shear force to the bending stress, right? So it is not that simple. So for that we want to adopt some generalized formulation, so that any kind of structure, any kind of model, we can use the same constitutive relationship, strain displacement relationship, and then a method to find the force also in that case. So however, like as Professor Amit Shah was mentioning in class, like there are various methods to approach this finite element method. However, I am not aware of any. I have only studied like whatever it was taught in class in those lectures, and I am also approaching through the same method, just giving you a brief overview of the whole thing. Okay. So now we know this constitutive relationship. We know some relation of the strain and displacement. So this strain and displacement, what we can do is we can generalize it in some form. We can say strain equals to B into D. Okay. And this B matrix is will be according to the system you have, right? So in this case, this B matrix would be something del x, then del something, del x 0 0 0 0, those things, then 0 del y. Like, please don't go by this. I am just giving you the essence. This is not the correct one, but something like this, right? This B matrix will be something like this. So we now what we can do is we can simply use the constitutive relationship. Okay, before that, now what is the strain, energy of this element? Now, why do we need the strain energy here? Why are we jumping to the strain energy? Again, because as you might recall, when I was discussing the shared deformation method, the shared deformation evaluation method, we use the energy based methods, right? So again, in this problem, again we will use the energy based method to find the forces in the different cases, okay, to find the force displacement relationship. So we use the strain energy. The strain energy of the element, say U, is given as half into integration over the whole domain epsilon transpose into sigma d integration. Yes. So this formula, it is from the strength of material or solid mechanics course you can find, but simply without that also, from basic understanding we can, and like we can realize that this formula, it's not that we can derive this formula by basic understanding, but we can realize, like if there is some displacement x and if the force is F, so stiffness is K, so half K x square is the like strain displacement. So similar to that, if strain transpose into stress, this is and half of that will give you the strain energy. Now from here, from the strain energy, we can easily put the values of epsilon and values of sigma. How? We know from the constitutive relationship sigma equals to d epsilon, and from strain displacement relationship epsilon is equals to b into d. So we have the formula like this: b into d, then transpose of that, then again d into epsilon, then d epsilon. Okay. Again, if we simplify one further step, b d transpose d, then again epsilon is b d sigma. Okay. Now if we integrate this thing, we have two d's. This might be same repetition of whatever was discussed in class. We have these two d's which will convert into one after integration, and then this half will go away. Okay. So what is now going to happen? Oh no, sorry. This is still here. This is okay. Now using the Castigliano theorem, as you might recall from the from our shared deformation discussion, if we do del u by del d, we have to take out one d. If we do del u by del d, what we'll get? We'll get the force, right? And that will be equal to summation of whole domain b d b d omega and then d. Okay. So this is basically the force displacement relationship which we were looking for. And here this is actually our stiffness, which we previously used is from the basic understanding of structural mechanics. We derived the stiffness matrix. Here we don't understand structural mechanics, but we know some methods how to arrive at that stiffness, and this is how we arrive at the stiffness, and we use it for our finite element method. So this is the basic development of the problem, like how it is moved forward. So this part is clear, like how it is done, why it is done, and those things. In very basic level, I don't
Yes.
expect anybody to understand from my from my explanation, but like very basic things like why it is done and how it is derived, those things may be clear. So doing this exercise, what are the things that we require basically? We know the domain, we can integrate throughout the domain. We know the D matrix, okay? We know the D matrix. Why we know the D matrix? Because we actually know what is the constitutive relationship from the strain stress strain relationship of the material. So D matrix actually comes from the material, okay?
D is basically material property.
Material property, exactly. So but the issue here is what would be the B matrix. Like this B matrix is the strain displacement relationship, and it will be actually correlated to this displacement vector, right? Like for different kind of displacement, the strain displacement relationship would be different, right? For there are different kinds of strains and displacements, deformations in the structural system, right? So it will be actually correlated to the displacement, okay? Displacement and also the geometry of the material. Geometry will decide what kind of strains will develop in the material. Like it could be I think you understand, like it could be a plane strain problem if the geometry is something. It could be a plane stress problem if the geometry is something else. So those things. So the basic, like we know the D matrix, the different modulus of elasticity and those things. What we basically need is the B matrix with respect to our degrees of freedom in the system, right? So if we have the B matrix, we know the D matrix, then B trans. Okay, I forgot to give a transpose here, I think. Okay. So B transpose D into B, integration over the whole domain, that will give us the actual stiffness of the system, and then it is pretty simple. Then it is pretty simple to similar to our matrix method analysis. So how do we find the B matrix? So again, the most simplest element which I could possibly take, I have taken that. So that is the bar element. Okay. If we say have a bar element, we have u1 u2. These are the two displacements, okay, at the 2 points. Say this is joint 1, joint 2, okay. Now our aim is to get a generalized solution of displacement at each and every point in this bar element, right? So what we can do is we can assume u at any point equals to a function of these two nodal displacements. Now we assume that the nodal displacements are our degrees of freedom. Now we, even from the terminology, we understand degrees of freedom means our bar element is free to like move in those directions at those points. So like u1 and u2 are our variables which will control the displacement response within that bar element, okay. So whatever displacement response we have in the bar element, that will be related to its nodal displacement. This is like what I feel is the second most important feature of finite element method. In finite element method, any kind of element, whether it is a bar element, triangular element, say square element, any kind of element, whatever is the element variable within the element, that is actually defined from the nodal variables, okay. So basically in finite element method, what we do is we discretize our structure into various portions, and we try to collect information at the different nodes. Okay, I hope you could follow. Like, we try to find the information at the different nodes, and using that information we use various interpolation function to find the uh, probable response within the nodes. Okay, so that is where comes the assumption. In case of analytical solution, we would know that what is the response within the nodes, what is the response at each point. But in finite element, we interpolate the response from different nodes. Basically, this is like the basic like core of finite element method. We discretize it into different elements. We take the nodal values, we interpolate it throughout the like throughout the span of the element as well. Okay, this part is clear.
Yes, yes,
Yeah.
yes.
So now, say for a very simple bar element, if we want to interpolate the nodal displacements within the bar element, what we can do is we can simply use the nodal displacements and generate a formula. Again, you have a lot of questions, I guess, in the assignment related to this, like what would be the appropriate formula to represent the displacements within the element, and that you might decide using like whatever information is available. Now this information is available is also like, this is also something which we have discussed, maybe using rank of matrix and those things when we have discussed. Like, these are the two independent informations, u1 and u2, that is available. So if we need to if we need to develop some function, we can only have two variables. Why two variables? Because we have two informations. So if we develop a function, say ux, we can equate those two, we can equate those function ux at 2 points, and we can solve it. So we can only use two different variables, not variables, two different factors in the interpolation function. So what would it be? A plus bxa. Okay, now how we will find the constants a and b? We will find u at x1 equals to a plus bx1 equals to u1, and u at x2 equals to a plus bx2 equals to u2. Well and good. So now so now I am actually not solving this. I am not assuming this as x equals to 0, x1 equals to 0, x2 equals to L. I am not doing these things. I just want you to understand the concept now. So now using these two equation, this is currently, these are two equation. If you go to some other problem, this will be more equations, right? So from these two equations, I can actually find ux in terms of u1 plus u2 with some things here. Okay, so this part is clear, this part is
Yeah, yes, yes,
understandable.
yes,
Yes.
yes.
So what are these are actually the shape functions. Okay, so these are the two shape functions corresponding to the two nodes of the two nodal displacements of the two nodes of the bar element. These are called the shape functions. Shape functions or interpolation functions is same terminology. Okay, so for a bar element it was only this. For a beam element, there will be four shape functions for a two noded beam element. Okay, because you have four information, you have the two displacements at the two nodes, two rotations at the two nodes, four information, you can actually have four different shape functions corresponding to the four nodal displacements. Okay, so now once you have the once you have this thing, say once you have the formula of ux equals to say n1 u1 plus n2 u2 plus n3 u3. I am keeping this now open ended. I am not talking about this bar element anymore. Okay, You have this ux. Now, from this ux, can you go to the uh, can you go to the um, strain displacement relationship to find the strain? Like from this is actually the displacement. Okay, ux is the displacement within the bar element. Now, what would be the strain within the bar element? Strain would be nothing but epsilon
To,
x. Pardon.
it is difference with respect to x. You need, if you differentiate that you will get that in
Exactly,
that particular
exactly.
direction.
So for bar element, it will be nothing but dn1 dx u1 plus del n2 del x u2 plus dot dot dot. Okay. For a bar element, it
And
will
if it
be
is two nodes, you will have a two shape function. If it is three nodes, you will have three shape functions.
if we have three nodes, we have
Six,
three. Yeah.
six, three or
If,
six.
huh, huh.
If it is a three nodes,
Hmm.
how many shape functions? It
We
will
have three
be
shape functions.
okay.
Yeah. The reason is like how many information you have at the nodes. You only have
Okay,
one information at the node, right?
correct. For a
So,
okay, agreed.
so for three information, you can take three constants. So similarly for beam, it is two node. It you will have four shape functions. If it is three node, you will have six shape functions. Okay, because you have two information at each node of the beam element. Okay,
Got it. Got it.
so now but in beam element it is not so simple that you write the strain as del n del x and those things. Okay, so that is why I have not taken beam element for the discussion because it would be difficult for me. Anyways, so jokes apart, so so for strain element we can understand very simply, like we have the displacement, we differentiate with x, we find the strain. So now we can write the strain say as a matrix kind of format for the different displacement. Okay, this is acceptable.
Yes, yes.
Yes, so this is nothing but the B matrix. So now we have the D matrix, we have the B matrix, you can easily find the stiffness of the element. Okay,
But the B matrix is only the derivative, shape functions derivatives.
yeah. B matrix would only be this one. I would not call this is the derivative of shape function because for different kind of problem it will be different, but B matrix is this.
But
Why?
basically, it's a shape function derivative. B.
In this case, yeah, in this case I am not sure about what will happen in other cases. Like it will be some kind of derivative of shape function, but it might be double derivative also and those things. If it is
Okay.
say theta and we are talking about the vertical deflection, so theta would be the double derivative, right? So we are not going into that. It is problem specific, but basically B matrix is this coefficients which are associated with the displacements to define the strain, right? Epsilon equals to hmm, epsilon equals to B into D. This was our basic strain displacement relationship. Epsilon equals to B into D. Okay. Okay, so this is clear.
Yes, yes.
So these are some of the basic concepts of finite element method. I know very little to say, but still these were, I felt that maybe if I
How this
explain this. Hmm?
size of the matrix related to global? Any idea?
Uh,
Is there any link?
can you please once more?
Because B is also a matrix. How
B is
that
also a matrix, yes.
how that matrix size related to global stiffness matrix? Can we?
Global stiffness. Okay, yeah, sure. So uh, basically, global stiffness matrix. Currently we are, this is actually the local stiffness matrix itself, right? This one, this B transpose.
See, for example, if you consider a bar element with the two
Hmm.
nodes, that the B matrix will
Um,
be 1 by 2 matrix, one row, two columns.
Mm. Yeah, I'm
for two
on.
node elements.
Yeah, just 1 second.
Yeah.
So this one is the stiffness, right? So
Yes. Yes. Yes.
what is the, like, is this the local stiffness matrix or the global stiffness matrix?
Uh,
It could be
it,
actually anything. Okay. Why anything? By anything I am not means, so say this is the bar problem. Okay.
because in FEM, I think global and local access will be same, right?
Yeah, yeah. Global and
It
local
cannot be
access.
different.
Yeah, means what I'm trying to say is like it's not like global and local anymore. Yeah,
Yes.
because you are already discretizing it into various small elements, and you are considering these each one as the independent
Should be in
degrees
the
of
same
freedom.
direction. Independent, it should be in the same directions. It cannot have two multiple
Yeah,
directions.
yeah, yeah. For bar element. Hmm. So these are each independent degrees of freedom that you are considering in the problem. Okay. So
Even if it
now,
is plate element, why do you think it should be different? Because your stress in x-axis and y-axis should be same in adjacent elements. It cannot be different.
stress in x-axis, y-axis.
Because anyway, you're interpolating between the nodes. It has to have a same axis. You cannot have a two different
Uh,
axes. Correct.
yes, yes, that is correct. But then, like, if it is a, say, a hollow cube kind of structure, okay. So there are six
Mhm.
plates at different directions. So then again, you have to kind of consider the transformation.
Okay. Okay.
Yeah. So um,
Need some
yes.
time to think. Man.
Uh,
Need a lot of
no
time
problem.
to understand.
Mm-hmm. So basically here it is actually the local stiffness matrix which we are getting by this. Why I am saying so is that this is actually the local stiffness matrix. Why? Because we are calculating the stiffness of this element, right? This element which we have considered,
Mhm.
we are calculating the stiffness for that element. Now in that element we are considering two nodes or three nodes, that is up to us to define the uh, to define the interpolation within that element. Okay.
Correct.
But
Correct.
still we are going element by element, we are not taking the whole bar at once and considering the whole bar as one element. There is a difference between this being one element and this being one element, right?
Correct. Correct.
Yes. So again, this stiffness is actually the local stiffness which we get. Okay. Then
Mhm.
we get many stiffnesses like this, and then we generate the global stiffness matrix. Okay.
But that size will be same for okay.
Huh,
It
now
depends
now
on again
coming to
the
the size. Now coming to the size. So the size will actually depend on the number of degrees of freedom in one element. Okay. So if it is one element, one bar element with 2 degrees of freedom, say u1 and u2, what would be the size? The size would be uh, size would be something like this.
B transpose will
Mm,
be 2 by 1.
this
D
would
will be
be 1
1 by 2.
cross 2, this was 2 cross 1, this would be 1 cross 1. D is 1 cross 1 because D is equals to the elastic modulus E, right?
Mhm. Mhm.
Only
Mhm.
one element, and only one axial stiffness, so only elastic modulus. And B transpose, B is actually this one, del n1 by x, del
Correct.
n2 by x, del
Mhm.
x, huh? So these are two elements. So two elements is one row and two columns. So when we take the transpose, two row and one columns. So now your stiffness matrix would be 2 cross 1
2
into
by
1 cross 1 into 1 cross
it
2.
will be
It
2
will
by
be
2. It will be 2
2
by
by
2.
2.
Fine.
2 by 2 stiffness matrix, which is actually the element stiffness matrix of a two noded bar element, as we know. Okay.
But for that,
Hmm?
okay, for a same bar, if it
Hmm?
is 3 nodes, finally it will be 3 by 3.
It will be 3 by 3. Exactly. Yes.
Okay.
Hmm. Okay.
Okay, if you increase the number of nodes, your global stiffness matrix, okay, of course, it will increase because
It
number
will
of
increase.
freedoms will increase.
Yes, yes. Basically, it is dependent on the number of degrees of freedom in one element. If the number of degrees of freedom in one element is say n, so our B matrix would be 1 cross. Okay, now again there is a difference. Like it will depend on like how many B matrix could be also more than like 3 cross 2 also, 3 cross 3
See,
also,
for
like
a,
that.
say,
Hmm.
for one bar, okay,
Hmm.
there will be multiple elements depending on the how many nodes I am considering.
Yes, yes,
Between the nodes, it is one element that will have a 2 by 2
yes, yes,
or
yes,
1 by 2.
yes, yes.
But if you consider the whole bar,
Hmm.
that matrix size will be big if number of nodes increases,
Big, yeah,
or
yeah,
it
yeah.
will remain.
Nah, the elemental
But your
matrix will be 2 by 2. Then
yeah,
they will be
exact.
assembled in global stiffness matrix. Global stiffness matrix would be 6 by 6.
Depending on the number of nodes.
Depending on the number of nodes, yes. Element assembly as we have done in the different truss
Correct.
problem or beam problem.
So as you increase number of nodes, your global stiffness matrix size will
Will keep
increase.
on increasing. Yes, yes, yes.
But in our matrix analysis, we studied that for a bar element, it will be a 2 by 2 matrix, right?
Yes, because we considered the whole bar as a single element. We did not break it down.
Okay. So again,
Hmm.
it is, I mean, if you increase number of, again, it part of a convergence law.
Yes. Hmm.
Okay.
Again, part of convergence, but like here we can get the actual formula, right? In for simple bar elements, so
Hmm.
it is not required like maybe to
Agreed.
discretize.
Agreed.
Yeah. Hmm. Anyways, so this was the discussion. Any more questions?
No, no, it takes a lot of time to understand these
Yeah, yeah,
things.
yeah, yeah, yeah. I
I
agree.
mean,
Hmm.
in 1 week,
Yeah, yeah, yeah. Still, I was amazed like how much Professor Shaw covered in like 1 week.
it is
Like,
too much for 1 week.
it
It is
was
too much.
it was a lot. I felt because even I am very like not very knowledgeable, and I found that it is very lot. But like I'm not sure whether lot of difficult questions will come from this part. The
No, that's okay. I'm not
objective,
worried about the questions actually.
yeah,
I'm not worried about
yeah,
the.
yeah, Hmm.
I crossed all that stage now, scoring marks.
Yeah, yeah,
So
yeah.
it is not for that. It is just to understand the
Yeah.
things that the thing.
Yes, yes. So moving on to the like previous year's assignment for this week 8 lecture. So first question is say how many independent stress components are there for a three-dimensional body? Now, I think we have already covered this
It
question.
is six,
It is 6, yeah.
three normal and three straight shear.
Yeah, yeah.
Correct?
Yeah, we have already covered this, right? The 6
If it is
6
a plane,
stress
it will
components.
be three.
Plane
Correct?
it will
Two
be
normal
3.
and
Exactly.
one shear. Okay.
Exactly, exactly. So, okay, let me quickly draw the components just in case anybody is interested to see it online. So, what are the components? Sigma xx, sigma yy, sigma zz, tau xy, tau yz, tau zx. 6 components. So next question is how many number of constants are required for a polynomial of shape function of a beam element? So again a pretty simple question. How many
Polynomial shape function of a
beam element?
It is four, two,
4,
4
right?
degrees of freedom. 4 degrees of freedom.
Yeah, 4 degrees of freedom, so 4 constants. We say v1 theta 1, v2 theta 2, 4 degrees of freedom, therefore 4
Is
equation.
it same as shape functions in that question? Number of constants required for a polynomial? Is it
Yes.
indirectly asking how many shape? What are the shape? I mean, number of shape
So
functions required,
uh,
or it is different?
it is actually same because it is just rearrangement of the problem, right?
No,
So
I'm just talking about the terminology.
no,
Instead,
terminology is
can they use the
different.
shape function
Terminology
in
is
this question?
this constant is different because
Okay,
it is asked that how many number of constants are there in the shape function.
correct.
Okay, so shape function itself is like n1 equals to something, say like a function of these v1 v2 theta 1 theta 2. Okay, so these are like the different constants. Okay.
Now, in that case, is it that the Pascal's
Yeah,
2n
yeah, yeah,
minus
yeah.
1? In that case,
Pascal's 2n minus 1.
correct? Is it
Uh,
3
2n.
constant? 2n minus 1, right?
I don't understand. What is the law? As far as I remember, the Pascal's law was like. Mm, okay, okay. Okay,
No,
okay.
I'm confusing with that integration,
Yeah, yeah, yeah,
numerical
yeah.
integration.
Mm.
Okay, got it.
No, no. Pascal was something else. Like here we know that there are 4 degrees of freedom, so we are trying to define a polynomial function
Correct.
for the we are trying to define a polynomial function for the deformation, which would be say something, say
You're
a
calling same A plus, correct.
plus bx plus c, say x
That is
c.
the same thing, right? That is the same Pascal triangle, right? That is the same Pascal triangle.
That is the same. So there, the Pascal triangle is something else. Like there, they tell you that what is the power, what is the order of the
Okay.
polynomial function,
Linear
and
equation, if it is a quadratic, I mean,
yes,
okay.
yes, yes, yes,
Okay.
yes,
If it is a quadratic, how many constants? If it is cubic equations, what is that number of? Okay, okay.
yes, 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 yes. So here, say this x cube plus x square plus dx cube, something like this. Okay. So now here we can afford to take 4 constants because we have 4 degrees of freedom.
Okay. We need 4 constant to solve that 4 degrees of freedom. Okay.
Yeah, yeah, yeah. Maybe with lesser number of constants could also satisfy, but then another, like if you have 4 information, you can have 4 equations to solve the 4 constants. That is the like motto. Okay. So it is directly correlated to the how many degrees of freedom do you have for the element. Okay. I hope this is understood.
Yeah, yeah.
Hmm.
This is for a beam element.
For a beam element. For a bar element, this would be 2, a 2 noded bar element. Yeah.
Will it be 6 for a frame element? 3 at each.
For a frame element, yeah, yeah, yeah,
Uh,
yeah.
2 transformation, 1 rotation.
Yes, yes, yes.
3, 6. Okay.
Hmm. Then for a single bar element at any intermediate point between the nodes, if n1 is equals to point 9, what will be the value of n2?
It
N1
is
and
point
n2 are the
1.
two.
It is
Point
point
1.
1.
Yeah. Why? Because n1 plus n2 equals to 1. This is a property of the shape function.
What is that property? I didn't get that property name actually. He said something. I forgot that name.
Uh, Property
Some
name.
specific name for that. I don't. I need to check that class again.
Yeah, I don't remember exactly. Maybe you can check the lecture again.
Yeah, yeah.
Yeah.
I'll just check that. Yeah.
Yeah. So next question is p-type convergence is associated with size
Order of
of
the
element,
polynomial.
order
Order
of
of
the
the polynomial.
polynomial. Yeah, exactly. So nothing to discuss here. Obviously, like p-type convergence means increase in the increase in number of like increase in the order of the polynomial. Then what will be the size of stiffness matrix if B is 3 cross 6 and D is 3 cross 3? It's pretty simple.
So,
B transpose D.
will it be 3 by 3?
No.
Because B transpose will be 6 by 3.
Hmm.
Okay, first term should be 6. Okay.
This is 3 cross 3. This is 3 cross 6. This is 6 cross 3.
So it will be 6 by 6.
6 by
Basically.
6. Yep. Okay. Clear?
But again, it depends on the different elements, bar element, because question says that B is 6 by 3.
Yeah. Question has given you the order of B. Like question just wants to know whether you know this formula or not. The question doesn't say that what kind of element is this.
Mm-hmm.
So this is clear, right?
Will there be any chance that, to answer the B transpose giving a bar element with 3 nodes or a frame like that? Any questions?
I am not
Or,
sure, but I would not expect something like that.
okay.
Because basically, if the question is from bar element, you are talking about finite element, right?
I mean, like this objective type, if they ask, okay, if it is a bar element with 4 nodes, what will be the B matrix or B transpose or a D matrix?
Okay.
Any such type of things? I
So
don't know. I'm just guessing. I mean, can
yeah,
it
but
be?
yeah. So I don't know the question, but this is pretty simple question, right? If it is a bar element, what would be the D matrix? It would be simple, one
1
one
by.
cross one.
If it is with 3 nodes, bar element with the 3 nodes?
Again, one cross one. Uh, if it is a bar element, basically in bar element, what you are
Okay, so it's a
fixing.
single element. Anyway, B is for a local, okay, same
Yeah,
element.
yeah,
Okay,
yeah.
okay,
You,
okay.
you are fixing the stress
I'm
and
just
strain.
confusing with this B and a
Only
global stiffness matrix. Okay, I'm just
no,
getting
no.
confused.
Yeah.
Okay.
So
So this
you
bar
are.
element bit is 1 by 1 it is. Okay, clear.
No, not for one element. I'm not talking about. I'm talking about the D.
Bar element.
Say for a bar element, the D will always be one cross one. Why it will be
Correct.
one cross one? Because you are restricting it as a bar. It has only one stress and it is related to the only strain using the elastic modulus. Okay.
Got it. Got it.
So you don't have the other stresses. So there it comes one cross one. Then depending on the number of nodes it has in each element, it will have that many order of B. Okay.
Okay. Okay.
Yeah. So okay. So the next question is, what will be the size of global stiffness matrix if the element of the following structure is considered beam element? Okay. So you have a structure like this, which is considered as a beam element. So in beam element, you have something like this.
Will it be 8 by 8 matrix?
8 by 8, yeah, perfect. So
Because
yeah.
increment node is a common. So
So
that means
none
that
of
we
them.
are going to add it up. Okay, none.
So four degrees of freedom into two. No, sorry, four nodes into two total degrees of freedom. And how many degrees of freedom? That many like elements in the stiffness matrix, 8 cross 8. Clear? Okay. How many nodes are considered in a constant strain triangle? In a constant strain triangle, how many nodes are considered? So by
Only
constant,
3. 3.
yeah, 3. So this is
Because we
a
are assuming strain is equal at 3. apex of the triangles. That is a
Yeah,
principle. Okay.
yeah, exactly. So if it is, say, um, so this is a triangle element. Now, if the strain has to be constant, then the displacement has to be linear.
So then 3 nodes should be enough, good enough
So
for that.
3 nodes should be good enough. So 3 is the correct answer. Uh, so here displacement equals to linear, that is ux equals to a plus bx kind of thing, and therefore the okay, so in triangle element I'm doing some mistake. uxy equals to a plus bx plus cy, so nodes are 3 nodes, will give us abc. Okay, now moving on to the next problem. How many terms will be there in an approximation of field variable in 2 dimension with quadratic polynomial according to Pascal's triangle?
Quadratic triangle 6. No, no, I have to check that triangle. 1 plus, I don't know.
So we have to like kind of check the
Quadratic, right? It is a quadratic.
quadratic.
It should be 6.
6, yeah, you are right. So 1 x y, then
X
x
square,
square,
xy square, x squared y, and y square.
yeah, square y,
Yeah.
x square,
Xy
y
square.
square. Uh, 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 uh,
No, 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 no. Xy square.
xy square y cube dot dot dot. So for this is constant,
Linear and quadratic.
this is linear, this is
So it will be 6.
quadratic. So quadratic will basically have all these terms. So 6 terms is the correct answer. Okay. So next is in finite element solution, the approximated field variable will converge from a lower value than the actual result, converge from a greater value than the actual result. Both of them are possible, none of them are possible. So what would be the correct answer?
Now what is that? Infinite element solution.
Field variable means, say, displacement or say something like that.
Uh,
This is the value
but it is none
of
of them, right? Because it can convert from larger value to lesser value. I don't know.
uh,
What is the
no.
meaning of larger value to smaller actual?
So this is, say, the value of the displacement. Okay.
Okay.
So these are the increase in the number of element,
Element. Okay.
or a increase in polynomial, increase in p value. Okay.
Mm-hmm. Mm-hmm.
So how will the solution converge? What do you think?
Now, what is the meaning of that larger to lower value to actual? Actual, I understand. What is that
Actually,
lower
you
value and
understand.
greater value
Like
in that?
it will go through here or go through here to converge.
Both of them are possible.
No.
Are lower value to actual.
This one.
Yes.
Now why?
Because element size will be less, correct? The displacement value will be low, because that's the, I'm just getting what is that lower and greater value.
Yeah,
What is the
it
meaning of that
means
lower
like
and
the
greater?
displacement will be low to and it will go higher, or displacement will be high and then it will go to lower.
This, I mean, obviously lower to higher, right?
Yeah, lower to higher. Why? Because the
Lower to
finite
actual, yeah.
element model
It
is
will have a lesser lesser displacement.
actually very stiff, right?
Yes.
So it like
Zero.
enhances the stiffness.
Practically zero. Then it goes to that actual value.
Yes, yes,
Rigid.
yes, yes, yes. So the size of element, if it is very small, then it moves to the actual value, and and it actually approaches from a very stiff solution to a more flexible solution. That was the concept on like why finite element method is gives you stiffer results, right?
Okay. So when we say lower value, it is the value of the individual elements to the, I mean, overall body.
Yeah, like it is I think it is clear in finite element solution the approximated field variable would be say something like a displacement or a rotation, something like that. So that will converge from a lower value than the actual result, or converge from a greater value than the actual result. So it will be lower, then it will converge, or it will be greater, then it will be converging.
It will be lower value to.
Yeah, yeah. Hmm. That was the question. Okay. So now the 10th question is, consider a polynomial fx equals to 1 plus 3x square. What will be the value of integration minus 1 to 1 fx dx using 2-point quadrature?
That is that
Okay.
equation 2n minus 1, what I said, right?
No, this
Yeah,
is using the Gauss quadrature method.
correct.
Yeah, yeah, yeah. Okay, okay, okay. You are talking about the you are talking about the like
Okay, number of.
which order to consider,
Yes,
right?
yes, yes,
Mm-hmm.
yes.
Gauss integration method.
So they again 2 points. I think we have to consider the third order and we have to take that values,
Yeah.
that weightage
So
of that.
fx equals to no, so second order itself, because it is written 2-point quadrature first of all, and second it is like x square, right?
Hmm.
So x square second order would give you like close to correct answer, I think. No, yeah, it is written also the 2-point curvature method. So 2-point curvature, what is that? I am actually not aware of the formula, so I have already copied the formula here.
That is that.
So 2-point curvature, it is at these 2 points with these two eight factors. Okay.
Mhm.
So what is this? 1 plus 3, 1 by root 3 square plus 1, 1 plus 3 minus 1 by root 3 square. So answer is actually 4. Okay. So this was all. Okay. Okay, so that was all the questions from last week also. Now, for the first time, maybe we have completed within time. We have 7 minutes on our hand. So, uh, do you have any other questions?
No, it is too much for a week.
Yes, yes, yes. But
And you have to have this solid mechanics background, all these
hmm.
plane space, plane strain. Then you'll understand
Mm-hmm.
fast these things. Otherwise,
Yes, correct. So that was all. So maybe we can end the class here today.
yes. Thanks. Yes.
Yeah, and thank you very much for sticking along for all the weeks, all the classes. And I hope that I could like give a little bit of knowledge
Yeah,
on
yeah,
these
definitely. I
things.
mean, I learned a
Yeah,
lot. Yes.
yeah, yeah. Okay, it was
Okay.
like nice having you and interacting with me during the class. And thank you so much, and thank you to all the other viewers also if somebody is watching through YouTube. And you can always like reach me through my email ID. I hope you have my email
Sure.
ID.
I have your email ID. Yes, yes.
Yeah, so any queries, this course will end in this Sunday, so I don't expect any more queries from this course. But any
S-
queries you for research or anything structural dynamics, vibration control, anything, so you can
Definitely, I will reach out to you if I have any dynamics thing. We'll be doing a
yeah,
lot.
yeah, yeah, we can have a healthy discussion.
Machine foundations and isolators designs for equipment.
Yes,
So we'll
yes.
be installing a lot of this vibration isolation springs
Okay,
for
okay, okay.
a lot of our equipments,
Are
compressors,
you
or
involved in the procurement of the
yes,
isolators? Okay,
yes.
so which company are you like?
Garb only I mean India, Garb. Yes.
Pardon?
Garb, GRB. They are the ones
GRB.
monopolized in this spring supply and design. I think they are basically
Oh,
from German company. You're not
oh,
aware
okay.
about that?
I am not aware about that company. There is one company in New Delhi, maybe most of India also, Hilti. Are you aware of that?
Hilti, they're giving this. They are
Connects
specialized in post-installed anchorage systems,
anchorage
basically.
systems and stuff. They also, I think,
Are
trying
they
to.
into this springs now?
I am not sure, but maybe they were
No, no, no. I think this Garb is the
not right now.
monopolized
There is one more
monopolized in.
company in New
They are
Delhi called Resistoflex. Have you heard about them?
they are there, but these people are monopolized in the market.
Yeah, yeah,
If
yeah, yeah. I
you
also think Resistoflex does that. I know shock absorbers and those things.
no,
All
I'm
the
talking about the okay. They're supplying. See, for small equipments, motors. I mean, there will be different things:
hmm
vibration isolation pads and vibration isolation springs.
hmm
When it comes to springs,
hmm
Garb is the one who have monopolized the market.
okay, okay.
However, isolation pad, okay. There are
Hmm.
dampeners. Even Dunlop gives something in what you call these rubber isolation pads. Even Dunlop provides
Okay,
that
okay, okay.
elastomer based thing.
Okay,
So
okay, okay.
lot of things. Okay,
Hmm.
so if you see any power plants, go to NTPC, BHEL.
Yeah, yeah, yeah.
These Garb people are the ones who supplying
Hmm.
these uh,
Okay,
springs
okay, okay.
for
L-
that.
have you come across any company supplying isolators for buildings in India?
No, but as I said, because this nowadays there are no demand for these thermal power plants.
Yes.
This even Garb is losing the market. Okay,
No demand? Why?
so
Like,
coal thermal power plant, no
oh, okay,
demand.
okay, okay. Yeah, thermal, yeah,
Thermal
demand for the
plant,
thermal
because
power
earlier
plant. I
these
see.
people are mostly dependent on these thermal power plants.
Oh, okay,
Since
okay.
there are no demand, so
Hmm.
these people markets are going down.
Oh,
So
okay.
they are shifting to building isolations.
They are shifting to building. Okay, okay.
Yes. They are
Yeah.
doing that.
Can you guess like any company which is a leading building isolator producer in Japan? In
No,
Japan,
no.
every like there is a lot of isolated buildings.
I know that. I know that
Yeah.
they have to. They
But
have to.
but I am telling you this information because it was very amazing to me when I heard the name. Because I know you know the name, but you could never guess that this company makes building isolators. Do you want to guess?
No, no.
Bridgestone. So,
Bridgestone.
yeah, Bridgestone, the same tire company that
I
you
know.
use,
Huh.
they are actually one of the greatest suppliers of building isolators in Japan, and
Okay.
they have proper building isolated design modules and technical manuals, and they have like just like
These are all standard build, right? It is
completely
not
standardized their
a.
product.
Yes.
Hmm.
It is not. We cannot design for a specific build. It is a standard. This is what we have to buy from them. Is this like
Uh,
that?
uh, I am not aware of the details, but basically for building isolators, design is like very specific to the building, but they have some standard ready-made kind of product. So as a designer, you can use those and then coordinate. Like
What they'll be isolating only at the foundation level, basically, or
that is
something
up to
different.
the designer actually.
Okay. Okay.
Yeah, so basically I am working like actively in the base isolation of structures and these things. So it is basically up to the designer. Everything is possible, only like you have to see what is the most feasible kind of solution.
Okay. Quite interesting to
Mm.
know those things.
Yeah, yeah.
But unfortunately, we're not getting opportunities in such type of designs. Okay.
Yeah, in
So,
India it is not so, like, not yet popular to use building isolator, and that is quite justifiable also in terms of the
no,
damage that
sometimes
has.
what happens,
um,
this
hmm,
building a vibration isolation system could
hmm, hmm,
be an option where, see, in refineries and
hmm,
gas fields,
hmm,
we'll be designing the control buildings for the blast resistance.
hmm, hmm, hmm,
Some
hmm,
they'll be doing
hmm,
some consequences studies of some
hmm, hmm,
vapor cloud burst or some other consequences that develop some blast waves.
hmm, 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 hmm. Yeah, that kind of work is also conducted in our laboratory in IIT Delhi,
Uh,
and yeah, like, and also mostly what we are focusing nowadays is, like, what my research focuses is, like, at least the hospitals need to be like base isolated or vibration controlled, because
Definitely, yes, yes.
because that is the, like, first source after a disaster for disaster management. So the hospitals need to be strong enough. So that is what my research actually revolves around. And also, like, for buildings during earthquakes, if it shakes, you move down the stairs, what will happen in the hospital? Like, you cannot expect the
Definitely,
patients running down the stairs.
yes, yes,
So those things, yeah. Maybe some of the hospital buildings, I know one or two. One in New Delhi, in Dwarka, one in Jammu and Kashmir, Srinagar, I think. So they are already like base isolated.
yes.
So maybe slowly we'll get base isolated hospitals in India also.
Okay,
Yeah.
definitely. So in future, if I need any help, I'll just be in touch with you for any help on this dynamics.
Yeah,
If you
sure.
need,
I'll be ready to help, and
if,
as always, like, it will be a open discussion. I also know very little, and we can discuss and solve. Yeah.
uh, okay, sometimes we'll
Mm.
not be knowing the basics of
Yeah. No, no,
some
no
of the
problem.
things.
Yeah. Yeah, I'll be
Okay,
very happy to help. Yeah.
definitely, I'll reach out to you, Mr. Banerjee.
Yeah. Okay. Thank you so much.
Okay, thanks,
Yeah.
Mr. Banerjee. Thanks for
Okay.
all your time. Okay,
Yeah.
thanks. Bye.
Thank you. Okay. Bye.